In this video we're going to look at how to characterize carbon in terms of sp2, sp3 proportions. We're going to do this using the carbon Auger peak, and this also involves differentiating data so that we can work out a D parameter that is characteristic of different sp2, sp3 hybridization, and this is calculated as the energy separation between the maximum intensity of the derivative of this Auger peak to the minimum intensity. So the energy offset between these two peaks and troughs in the Auger signal when differentiated is an indication of the type of sp2, sp3 hybridization in carbon. If we apply these calculations to graphene oxide, for example, then it's possible, and this is an example, of the D parameter being used to calculate the different proportions of sp2, sp3 hybridization for a material that originally was graphene oxide that was then reduced in a systematic way to produce a pattern over the surface of a material. So there's a variation in this hybridization across this field of view, and by calculating spectra at each one of these pixels and calculating the D parameter, we're able to see this variation across the image. And just to illustrate that there is variation, that if we take the relative proportions of oxygen and carbon over the same imaged area, we can see that there is a pattern quite clearly there, that you have a predominant carbon zone and then a predominantly oxygenated zone as indicated by the green colouring. And the real problem when we want to do this type of calculation in terms of the D parameter is the signal to noise that we have in the data. These are real data measured from the sample. These are the raw data, and if we just directly differentiate these raw data using a 5-point quadratic Savitzky-Golay, then we end up with differentiated spectra that are incredibly noisy and not very open to a calculation of a maximum or a minimum in the signal over the energy interval of interest. So this is why in this video we're going to look at different techniques other than the basic Savitzky-Golay type differentiation that will allow the calculation of images as we saw earlier. The problem with random noise in a spectrum is that the variations that we see in the noise would translate into significant values for a derivative. So rather than trying to differentiate the data directly, Savitzky-Golay approximates the data by polynomials of various degrees, and by differentiating the polynomial you end up with an approximation that is hopefully less susceptible to noise. However, when you have such poor signal to noise as we see here, the Savitzky-Golay approach fails to actually produce a decent derivative from data if simply applied in the basic form. So what we're going to do is construct a curve that approximates these data, and then the way that curve is created, it'll be based on a peak model where we sum all the components in a peak model to produce the curve that represents the data, and then we can differentiate the individual components within the peak model to produce an overall derivative for the data that is far more precise than if we simply used the Savitzky-Golay method. The peak model that will fit these data is not intended to be physically meaningful in the context of carbon Auger signal. It's simply there to create a smooth curve that approximates the data. I've already prepared a file that contains such a peak model, and when I load this file it provides me with the peak model, and you can see that there are a set of bell-shaped curves. In fact, these are all Gaussian curves. That's the first indication that these are not physically meaningful, and they have been ordered in position. There are a set of offsets. These were simply determined based on one particular spectrum and found to apply equally well to others, so there's no real meaning to the fact that these have offsets in energy, and also the full width half maxima are all linked, so they all have the same full width half maximum. This emphasizes the idea that when we sum all of these, all we're doing is creating a single curve that models these data. But in the context of how I'm going to create this derivative here, it also provides me with a set of components that are well-defined mathematical forms which I can differentiate. And once I have the derivatives of these mathematical forms, I can then sum them using the relationships we see in the peak model, and that sum of derivatives is what will create the shapes we see here. The option that I'm going to use to differentiate these components is on the test data property page of the spectrum processing dialog window. And it's this button here that says replace by diff, meaning differentiation, component index. And the component index is related to the component index on the quantification parameters dialog window for each component. And what it will do is it will differentiate all the components with the same component index. So I demonstrate the set of components that we see here within the quantification parameters dialog window, the components property page. They are all assigned unique component indices, and that's for display purposes. So the components that we see here are colored according to the component index for each one of these individual components. But to perform the operation of differentiation, I need to set all of these to be the same. So in the first instance, I'll say reset. That will reassign the component index of each component to be -1. I can set that to be a different color by saying set equals, let's say 3, for example. And so the color that is displaying all of these components is now this same color that corresponds to the component index 3. But this is important in terms of replacing the data. So the spectrum itself will be replaced by process data that will be calculated from the derivative of each one of these component functions with the same component index. So having set up the component index so they're all the same, I can now perform the calculation on these data. So I press replace by diff comps index. And what has happened is the spectrum is replaced by the derivative of all of those components in the peak model. If I turn off the components, it will be clearer that these are in fact, and also the annotation, the same result has occurred as we saw in the previous example here. This was derived earlier from the same data, so I've gone through the steps that were necessary to create the derivative we see here. The next step is to preserve the derivative so it's no longer just the process form of the VAMAS block. I can do that by selecting the VAMAS block, which is already selected, and then using the copy with process data only, and that will produce the new VAMAS block containing the process data only. Let me display both of these. So this is the VAMAS block from which the new VAMAS block was created, and the difference between the two is that on the annotation history there's an entry indicating that this one has been differentiated based on components with a component index of 3, and if I reset that or undo, we go back to the original spectrum. On the other hand, the processed data when copied has no processing history, so this is now a permanent record of the derivative. You may have noticed that the spectrum that I've differentiated has rather good signal to noise, and the reason it has good signal to noise is it has been pre-processed, and it does derive from the original data set where the noise is quite significant, but the pre-processing that has been performed on these data is based on principal component analysis and noise reduction of an entire data set using the information about each spectrum within the data set, and the number of spectra that are actually in this data set are 16 times 18, so that's a significant number of spectra, and if we were to add all of those spectra together we would get good signal to noise for the one spectrum. But by using principal component analysis we can work out the number of significant shapes to these data and then reproduce each spectrum using a limited number of principal component abstract factors, which has the effect of reducing the noise. And this is very different from trying to smooth individual spectra to work out a better shape for each spectrum. We are using the information that is in the entire data set, the acquisition time of the entire data set, to reduce the noise in individual spectra based on an understanding of what noise looks like in the entire data set. This data set is set up so it can be processed using the image processing dialog window. However, what I'll do now is process these data using the PCA option on the spectrum processing dialog window, which requires me to change the format of this file from each VAMAS block containing 18 spectra into having individual spectra within each VAMAS block and having many more VAMAS blocks. So what I need to do here to create a new file is to overlay the set of VAMAS blocks that I would like to extract the data from, bring up the image processing dialog window and go to the VAMAS info property page of the image processing dialog window and apply convert CV to VB. This means convert corresponding variables to VAMAS blocks. So each corresponding variable, that would be the 18 different spectra in each one of these VAMAS blocks, will be used to create a new file that contains one VAMAS block per corresponding variable. So what we see now is a VAMAS file that contains multiple VAMAS blocks per VAMAS block in the original file, and this gives us access to the data in a way that allows the use of the PCA options on the spectrum processing dialog window. Principal component analysis involves transforming a set of spectra into principal components that are a mathematical form of the data that orders the data in the order of variance within the data. And the idea is that systematic signal will move to the front of the list and random noise will move to the end of the list. So to perform an analysis of this entire data set, I need to overlay the spectra in the active tile. And then using the PCA property page, there's a parameter that says the number of factors, and this represents the number of factors that will be calculated when I perform the principal component analysis. There's also an option that says use RMS. This is typical for a principal component analysis to use the root mean square, so we'll leave that active, and to perform the analysis of these data I'll press the generate factors button. The data set is then processed and it will calculate 12 abstract factors because that is what I've requested. So the iterative singular value decomposition that is used to calculate the PCA for these data allows the calculation of a specific number of abstract factors rather than all abstract factors that would be required for such a data set as this. This would be quite an extensive calculation if you wish to calculate all the abstract factors for these data. So the fact that you can reduce the number of abstract factors that you calculate reduces the time you wait to get the result. So now we have the abstract factors in the process form of the data for each one of these VAMAS blocks. Only the first 12 have genuine abstract factors. The other VAMAS blocks all contain a partial calculation of the singular value decomposition that would be required to generate all of the abstract factors by only calculating 12 abstract factors. If I display these now in a scroll list, we see the first abstract factor looks very much like a spectrum. The second one, well, this has a shape which is certainly not a spectrum, but it is significant to these data. The third abstract factor, well, it has a dip, so this could be some sort of shift that's occurred. And the fourth one, well, that looks like noise. So based on simply looking at the shapes within these abstract factors, we end up with an idea that maybe 3 abstract factors are sufficient to reproduce all of these data with the type of precision you'd expect for pulse counted data. So let's return to the top of the list and overlay these abstract factors again. We'll return the abstract factors to spectra, and the fact that I decided there were 3 that were significant means that I can now calculate for all of these spectra a least squares solution to all of these spectra based on the first 3 abstract factors, ignoring the rest as noise. So when I press the predict button, the calculation is performed and we end up with spectra that look more like the data that I used to do the differentiation. So these data are now in a form where the analysis can proceed peak fitting and then differentiating based on the peak fits, but that whole process is being supported by the fact that we've been able to use the information in this data file to remove a significant proportion of the random noise within these data. When we've calculated the noise reduced form of the spectra, one way to investigate how well that operation was performed is to display the residual. And the residual shows you the difference between a data envelope, which in this case the default for the data envelope is the raw data, and the spectrum, the current spectrum in the VAMAS block, in this case the process data. So the residual is showing you the difference between the process data, the PCA calculated data, and the original spectrum. And if we have pulse counted data, we would expect the residual standard deviation to be close to unity, and that is what we find with a relatively nice looking residual plot. That is to say, it's reasonably uniform across the entire range. So this is suggesting the PCA calculation using 3 abstract factors has produced a reasonable result for this particular spectrum. This file now contains the PCA enhanced data. So to preserve these data with the PCA benefit, I'm going to copy to a new VAMAS file the process form of these data. So when the copy is selected, I tick the box that says process data only. I have all the VAMAS blocks in the previous file selected. This is an empty file, so when I press OK, the process data is then moved into this empty frame. So now these are preserved. They cannot be undone. The form of these data are now such that we could construct images or fit with components. So let's fit some of these with components to illustrate how that might be done. I've got in the previous file a spectrum that contains a peak model. So if I display the components again, we see here we've got these represent the components all fitting the data with the envelope that fits the data very well. In fact, now we can see from the residual that the fit here is far too good in terms of a residual standard deviation, and that's the indication that this is processed data and not pulse counted data. So I've got this VAMAS block with the peak model. If I go back to my newly created file, I've got the first column selected. I could do the whole file. I'll just do the first column because it'll take a long time to peak fit all of these data. So I go back to the file that contains the spectrum with the peak model, and if I right click, I can propagate regions, components, and I'll say auto fit. So the background, the components in the peak model are now going to be transferred to the selected VAMAS blocks, and the fit performed by virtue of this button here that says auto fit components. And the operation proceeds, and when it is completed we can go back to the file that contains the selected VAMAS blocks. The display mode still does not have the regions selected. Now it does. I can even turn off the use of the component index to color, so we can see the components individually. I will just make that my default setting, so when I change VAMAS blocks I keep the default display setting as what I see here. And now you can see that each one of these spectra, as I step through these spectra, they all have a peak model that is fitting the data with good precision, mostly indicated by the uniform residual. So the final step, if I wanted to differentiate this first column, would be to go to the test data property page and replace by the differentiated spectrum with a component index. Let's see what the component index is. It's still 3, that's good, so I select one of these to indicate this is the component index that I want to perform the differentiation upon, and then press the button replace by diff comp index. So now I have a spectrum that is differentiated. The peak model, you can see, sits there on whatever the background currently is, but the thing of interest is this differentiated spectrum. And if I want to do this for other VAMAS blocks in this file for which a peak model has been defined with the same component indices, that's exactly what I've got in the first column, I can select the VAMAS blocks, right click, and this time I'm going to just propagate the processing operation. So this will now propagate the differentiation of the peak model for each one of these VAMAS blocks. Let's deselect the one that's already done. And propagate without auto fit. If I overlay all in the first column and again remove the display of components, we now have a set of spectra that are in a format that we could perform an analysis based on the D parameter.